Bickel from Bucknell University, who will talk about two-variable model spaces and associated realizations. Welcome.
Thank you. First, I guess thanks to the organizers for letting me speak, and also for putting together this phenomenal program that's spanning throughout the fall semester. It's really exciting to have this go on. And thanks to the participants who are here, it's a little intimidating to be talking to all 96 of you, especially because it turns out I can see the chat and my slides and me, but I can't see you. So if you have a question, I think if you put it in the chat, I'll be able to see it. But if you want to verbalize a question, you're just going to have to unmute yourself. I don't think I'll be able to see raised hands or anything of that nature. Okay, so I guess my talk today is going to shift topics a little bit from the purely one variable setting to the two variable setting. And the goal of my talk is hopefully to convince you that there are some interesting realization or representation formulas for two variable inner functions that arise from kind of the two variable analog of the one variable model spaces that Stefan has been teaching us about. So before jumping into the two variable setup, I really wanted to talk a little bit about what happens in the one variable setting and kind of what moves over to the two variable setting in a reasonable way, and where some of the hiccups occur. And so when I put together these slides, I thought presumably this slide and maybe the next one would all be review, but since it's a morning in the summer, maybe we should kind of walk through this anyway. So just as a reminder, when I say the Hardy space on the disk, I mean the set of functions that are holomorphic on the unit disk, so that when you write them as their power series centered at the origin, the coefficients that appear are square summable. And then when you have the Hardy space, kind of the natural operator to define on it is the shift operator, which of course Stefan talked about quite a bit in the last talk. And one way, I guess I'm using maybe slightly different notation, so that's something to watch out for. MZ is going to be the shift operator in this talk, and it's simply multiplication by z. So you take a function in the Hardy space and multiply it by z. Or equivalently, as again Stefan pointed out, if you look at what it does to the power series coefficients, if you write f as the power series centered at the origin, then all it does is shift them forward and put 0 in the first slot. Excuse me. The other object that kind of shows up in this circle of ideas, of course, is the concept of an inner function, because this is a week about model spaces. And so just a reminder, when I say an inner function, I'll mean a function that's holomorphic on the unit disk and has radial boundary values that equal 1 almost everywhere on the unit circle. And so just like Stefan, I'll be using t to denote the unit circle, and later on t squared to denote the unit circle cross itself. Now, later on in my talk, I'll be looking specifically at rational functions. So it's worth pointing out that in the one variable setting, the functions that are both rational and inner have a very nice form. These are just the finite Blaschke products. So you simply form those by taking these linear factors that are constructed by picking points on the unit disk and multiplying them all together. And up to a unimodular constant out front, this gives you the entire set of finite Blaschke products, or equivalently inner functions that are also rational in the one variable setting. And again, as Stefan mentioned, the theorem that ties all of these things together is Berling's theorem, which tells us that if we look at the subspaces of H2 formed from these inner functions, simply by taking an inner function phi and multiplying it by H2, then this collection of subspaces is exactly the set of subspaces of H2 that are invariant under the shift operator, or equivalently invariant under multiplication by z. All right, but since this is a talk about model spaces, we don't want the shift invariant subspaces. We actually want the backward shift invariant subspaces. So particularly to get a model space associated to an inner function phi, we take that shift invariant subspace theta times H2 and take the orthogonal complement of it inside of H2. And that will give me the model space K phi. So the notation I'm using here is similar but slightly different from Stefan's. My inner functions will be given by the variable phi, and my model spaces are K sub phi, but they're not scripty. So there's just some slight difference here. Now I want to take just a brief interlude here and remind you all about some properties of, model spaces, I suppose, but just more generally, reproducing kernel Hilbert spaces. So first, let's just recall the definition of a positive kernel. So a positive kernel on a set omega is a function defined on omega cross itself, so that when you pick any finite collection of points in omega, so that's this Z1 through Zm, and you form a corresponding matrix whose ijth entry is just the kernel evaluated at the point Zi and the point Zj, then you always get a positive semi-definite matrix. Now, if you start with a kernel function, then you can use this to build a Hilbert space of functions by basically allowing the first slot to be your variable and fixing the second slot to get a collection of functions that are only defined on omega. And if you take linear combinations and define your inner product in the right way, then you get a Hilbert space of functions, so that this kernel function that you started with is actually the reproducing kernel of that Hilbert space of functions. So what I mean by that is that if you take any function in the associated Hilbert space and inner product against your kernel function with the second variable fixed, then you will exactly get that function evaluated at, well, whatever you fixed the second variable at. So this kernel function gives you a way to evaluate functions inside of your Hilbert space. And kind of the critical thing for us is that you can move back and forth between positive kernels and reproducing kernel Hilbert spaces. If you have a kernel, you have a reproducing kernel Hilbert space, and if you have a reproducing kernel Hilbert space, you have a positive kernel. And if you do something to kind of one of these objects, it induces some similar transformation to the other object. So just as one instance that will show up later in my talk, if you have two positive kernels, say K1 and K2, defined on the same set omega, and add them together, you'll still get a positive kernel just by, basic properties of positive semi-definite matrices. And so then you have a collection of three reproducing kernel Hilbert spaces. And you can think about this space whose kernel is the sum of the two kernels as basically being the sum of those two Hilbert spaces, where every function in h of k is the sum of a function in hk1 and hk2. And there's a nice connection between the norms of these three Hilbert spaces. So the important thing for us later will be kind of adding kernels together, for example, and getting kind of new kernels which induce new reproducing kernel Hilbert spaces. In the setting of model spaces, of course, a model space is a reproducing kernel Hilbert space. And as Stefan told us, this kernel has a very nice form. It is just this function here that involves a difference with the inner function in the numerator, and then its denominator comes from the Cauchy kernel. All right. So as I mentioned earlier, it's kind of the main piece of my talk, or the goal of my talk, is to look at ways of representing two variable functions. But I want to tell you what happens in one variable, because it really does motivate the questions that we ask in the two variable setting. So instead of reading kind of this definition top to bottom, I want to start in the middle. And so what do we have here? So we have a contraction U, and it's going to act on the complex numbers plus some Hilbert space M. And we're going to take U and we're going to write it as a block operator. So A takes C to C, B takes M to C, and so on. Now, if you have a contraction like this, you can use it to just write down this formula here. on the right-hand side of that equation using just A, B, C, and D. And the formula that you get is called the transfer function of that operator U. So what this statement is saying is actually if I have an inner function, then every inner function is the transfer function of some operator U, some contraction acting on the complex numbers plus some Hilbert space M. And you can further choose this operator to be, nice, or by nice I mean either an isometry, a co-isometry, or a unitary. Kind of as one aside, so here I'm restricting to inner functions, and I'll do that throughout my whole talk. But as I think was pointed out in the chat, you have an analog of model spaces called de Bruijn-Rovniak spaces for functions that are not necessarily inner, but bounded by one on the unit disk. And a lot of the stuff that I talk about today, though not all of it, will extend to de Bruijn-Rovniak, or to Schur functions or de Bruijn-Rovniak spaces. Some in the one variable setting and some in the two variable setting. But I'm really just going to brush that under the rug because this is a model space week. So for me, everything is an inner function, even though you may have seen these results presented more generally in other settings. All right. So with that aside, every inner function has a transfer function realization. And I bolded co-isometric here because the co-isometric transfer function realizations are particularly nice. Oh, I went too far there. It turns out that if we require U to be a co-isometry, then, well, we can choose this Hilbert space M to be the model space. And A, B, C, and D have particularly nice formulas. So A is just taking a number X and multiplying it by phi of 0. B is taking a function in our model space and evaluating it at 0. C takes a number and multiplies it by the backward shift of phi, and it turns out that that is a function in the model space. And D takes a function in the model space and applies the backward shift, which of course maps back into the model space. And up to some unitary equivalence, if you define an appropriate notion of minimality, then every minimal transfer function realization is unitarily equivalent to this one. I don't want to belabor this point, but in this 2012 paper by Ball and Bolotnikov, they go through not just this co-isometric realization, but also the isometric and the unitary cases for a general, first one variable inner function phi. And then later they talk about some of the things that are known in two variables, but I'll talk about that part later on. But if you want to see more details about the one variable case, I'll direct you to that paper. One other thing is that if you end up getting bored in my talk, which is fine, maybe try and show that if you take this particular A, B, C, and D and just plug it into the transfer function realization formula, you actually recover your inner function phi. It's just a cute little computation that it turned out I didn't quite have enough time for in my talk. All right. So, even in Stefan's talk, we saw that a lot of kind of function theory questions end up getting shifted to the boundary and trying to understand how the functions behave on the unit circle. And so it kind of makes sense to ask, well, we have this nice realization formula that holds for points in the unit disk. When does this realization extend to points on the boundary of the unit disk? And it turns out that if we look at, trying to extend this realization to an arc on the unit disk, so some using I as intervals, of course you can think of arcs as intervals on the unit circle, then you can extract the answer from Saracen's nice book, Subhardy Hilbert spaces on the unit disk. And so he showed that the following, or his book includes the fact that the following things are equivalent. The first is that this I minus tau times the backward shift inverse operator is actually still a bounded linear operator on the model space for all points tau coming from this arc on the unit circle. And you should notice that this backward shift, that's just our D operator. And as long as that operator is a bounded linear operator on the model space, well then this right-hand side of the transfer function realization formula extends and makes sense at that point tau. So it's really getting that, inverse operator to be a bounded operator that's the kind of the hiccup and potentially extending the realization formula. Okay, and that ends up, being well defined as long as precisely when every function in the model space extends analytically past that arc I, which occurs precisely when the inner function extends analytically past the arc I. And it turns out that, inner functions extending analytically is morally equivalent to them extending continuously to that arc and having modulus 1 there, because you can do a kind of Schwartz reflection to extend them kind of automatically as long as they extend continuously. So really the conclusion that we get is down here. The realization formula extends to an arc on the unit circle precisely when our inner function extends to be continuous on that arc. So the regularity of the realization exactly reflects the regularity of the inner function. And that's really the kind of idea that we were hoping to generalize in the two variable setting, which I'll start introducing now. Okay, so there's lots of different two variable settings, but the two variable setting that I tend to live in is the bidisk. So a set of pairs of points in C2 where both coordinates have modulus less than 1. All right, so if you're in this setting, we can define all of the standard objects that we saw earlier in just a slightly different way. So the Hardy space on the bidisk is still the set of functions that are holomorphic on our domain, so that when we write them as a power series, the coefficient centered at the origin, the coefficients are square summable. It's just that now, our coefficients are indexed by both the power of Z1 and the power of Z2, so we have a doubly indexed sequence of power series coefficients. And again, we can still define the shift operators. These are just multiplication by the independent variable. But now we have two independent variables, so we have two shifts, an MZ1 and an MZ2. We can also still define inner functions. So these are, again, holomorphic on our domain and have a modulus bounded by 1. But when we look at where we want their radial boundary values to have modulus 1, we actually go out to points on the tutor. So we require both coordinates to have modulus equal to 1 if we require the function to have modulus equal to 1 there. So kind of the point is that if you think about the boundary of the bidisk, that's not what I wanted to write, there's also two faces to that boundary. And we don't worry about them so much. We really focus on what's called the distinguished boundary of the bidisk, which is the unit circle across itself. So, trying to generalize the notion of a finite Blaschke product, we can look at inner functions that are also rational in two variables. So here's one example, but unfortunately, there's not a nice formula for kind of the collection of all rational inner functions in two variables like there is in one variable with the finite Blaschke products. There's a way to generate them using polynomials that don't vanish on the bidisk in a fairly straightforward way. But we don't have a formula like that for finite Blaschke products because, of course, two variable polynomials don't factor into linear terms, and so there's only so much you can do. And similarly, we don't have Berling's theorem. These subspaces of the form our inner function times this two variable Hardy space are still invariant under the shift operator, so both Z1 and Z2. But those aren't all of the shift invariant subspaces. There are a lot more, which I'm going to completely ignore for the purposes of this talk because we're looking at inner functions. And if you fix one inner function in its generated shift invariant subspace, then you can, of course, define an associated backward shift invariant subspace by taking, the shift invariant one and then taking the orthogonal complement of that inside of the two variable Hardy space. And so then this model space that we get will be invariant under the backward shift in both Z1 and Z2. Now there is a useful property that shows up in the 2-variable setting that isn't really required in the 1-variable setting. So in the 2-variable setting, we have what are called Agler decompositions. So these are positive kernels. Okay, well, K1 and K2 are called Agler kernels. The decomposition, I guess, is this formula here. So an Agler decomposition means that you have two positive kernels, K1 and K2, so that this start equation holds. So you basically have this decomposition of your inner function in terms of two positive kernels combined with these two differences. Now, of course, if you were in the 1-variable setting, then maybe you would just think about having just like a 1 minus ZW bar. If you moved that difference term over, you would just get the formula for the reproducing kernel of the model space. And so this kind of formula would be somewhat trivial in the 1-variable setting. I mean, if it exists, it's just moving the denominator of the model space kernel over to one side. But it's not trivial in the 2-variable setting. I'm being told to leave the meeting somehow. Is that happening to anyone else?
Not really.
Hi, can you still hear me?
Yeah.
Yes, absolutely.
Okay, great. I'm getting an error message that I'm just going to ignore because you guys can still hear me, and that's kind of what's important. But if something ever happens, let me know in the chat. Okay, but the point is that this Agler decomposition really gives us a decomposition of the model space into two Hilbert spaces. So if we take this Agler decomposition formula here and just divide over, I'll get rid of that, the two difference terms, so the 1 minus Z1W1 bar and the 1 minus Z2W2 bar, we get this term here, which is the reproducing kernel of the 2-variable model space, plus these two kernels here. Now, instead of thinking about this as an equation involving positive kernels, we can think about this as an equation involving reproducing kernel Hilbert spaces. So really what this Agler decomposition is doing is it's giving us a decomposition of the model space into two Hilbert spaces, which I'm going to call S1 and S2. And these Hilbert spaces come with a particular structure. If we look at the reproducing kernel, say, of S1, the fact that it has that 1 minus Z1W1 bar in the denominator tells us that the associated Hilbert space is actually invariant under multiplication by Z1. And so we have something similar as well for S2. So this gives us a decomposition of the model space into a Z1 and Z2 invariant Hilbert spaces. Now, we often want a more concrete decomposition, and particularly one that gives us not just kind of sub-Hilbert spaces, but actually subspaces of the model space. And a really nice way to construct this decomposition appears in work by Balzadowski and Vinnikov, who basically get the subspace decomposition in this particular concrete way. So they define S1 max to be the maximal Z1 invariant subspace of the model space, and S2 min to be basically what's left over to be the orthogonal complement of S1 max inside the model space. And so you get this decomposition of the model space into these two concrete subspaces. One is invariant under Z1 and one is invariant under Z2. And if we form these kind of two maybe wandering subspaces, is I guess what they're called. So you take S1 max, apply the shift, and take the orthogonal complement of that inside of S1 max. Well, you'll get a reproducing kernel Hilbert space. And so you can extract the kernel, and that ends up giving you kind of one Agler kernel. And if you do the same thing to S2 min, you get another Agler kernel. So this gives us a concrete way of constructing a pair of Agler kernels associated to an inner function. And this is actually a construction that requires phi to be inner and not just a sure function. Okay, so how does this help us? Well, it's kind of the existence of Agler decompositions was really what led to the development or the proof of the existence of transfer function realizations in the two variable setting. So this and kind of getting an Agler decomposition type formula appeared both in work by Agler in 1990 and in the engineering literature by Anton Kumert in 89. And so what this says is that, well, every inner function has a transfer function realization. So that means that there is a contraction U that maps some C, the complex numbers plus some Hilbert.
Okay, it seems that now we do have genuine technical problem. Let's see if Kelly can reconnect soon.
I'm back in here. I don't know if you all can hear me or re-spotlight me or anything of that nature. I think finally, whatever technical difficulties my computer was yelling at me about, it finally got very angry. But it's good to be back, and sorry for the delay. Okay, so did you all hear me start talking about this slide? I don't really know when I cut out exactly.
I think so, Kelly. I heard you.
Okay, thanks, Joe. Okay, great. All right, so the point is that every inner function on the bidisk has a transfer function realization. But I need to tell you exactly what changes moving from one to two variables. So we still have this contraction U that's defined on C plus M to C plus M. And you write U as a block operator and plug its A, B, C, D operators into this transfer function realization formula. But of course, there's something slightly different going on because now we're in the two variable setting. And in particular, there's this EZ operator. So what that represents is that in order to have a two variable transfer function realization, our Hilbert space M had to be equipped with a direct sum into two pieces. So an M1 plus M2. And what this EZ operator is doing is it's feeding in an element from M, decomposing it into an element from M1 plus an element from M2, multiplying the first by Z1 and the second by Z2. So this is kind of our version of multiplication by Z in the two variable setting. All right, and just the existence of these transfer function realizations without a lot of information about maybe, you have some information about the underlying Hilbert space. We know it comes from the Agler decompositions plus some maybe extra piece. But, there's not kind of a concrete formula for all of the ABCD operators like we had in the one variable case. And even without like those specific operators, people were able to use these transfer function realizations to really move a lot of results on the disk to results on the bidisk. So just as an example, some examples, Jim Agler used this in the early 90s to develop Nevinlin pick interpolation on the bidisk. Greg Neese used it in 2007 to prove a version of the infinitesimal Short's lemma on the bidisk. Agler, McCarthy, and Young used this in two papers in 2012 to both generalize the Julia-Carthy-Adori theorem to the bidisk and also to generalize Livner's matrix monotonicity theorems to the two variable setting. And then recently I've been working with Greg Neese and James Pascoe and Alan Sola to quantify the boundary behavior of two variable rational and rational inner functions. And one kind of critical tool has been the existence of nice transfer function realizations. So just having them, even if we don't have all of the details, has proven really vital. And one of the reasons for this is that when you move to the 2-variable setting, a lot of the standard 1-variable tools just vanish. So we don't have an inner-outer factorization anymore. And even if you're looking at inner functions, you can't factor them into an infinite Blaschke product that carries the 0 behavior and a singular inner function. And so people turn to these other representation or realization formulas because the standard ones no longer apply. All right, so now I want to get into some of the properties of 2-variable realizations. And just as in the 1-variable setting, kind of my motivating question is, how do the properties of the inner function connect to the properties of its realization? Well, the simplest inner functions are our rational inner functions. So why don't we start with those? So here is the rational inner function that I mentioned earlier. So just super simple. It's degree 1 in Z1. It's degree 1 in Z2 as well. And so you can actually write down, a concrete transfer function realization for it, where your U here, I'm just gonna split it into the ABCD, is a 3x3 matrix. And in particular, D is 2x2. So that tells us our M is dimension 2. And if we look at the EZ operator here, you can see that the M1 has dimension 1 and M2 has dimension 1. So you have this really nice finite dimensional transfer function realization for this specific rational inner function. And it turns out that you have pretty simple transfer function realizations for all rational inner functions. Specifically, the degree of the rational inner function, so in this case it was 1, 1, transfers pretty much immediately to give you the dimension of the underlying, Hilbert space M. And so this appeared, so Greg Neese had a really nice proof of it in 2011, but he cited the original argument as, or the original kind of statement being encoded in Kummert's work from 1989. There are other results if you take your rational inner functions to be matrix valued. So again, Neese has a really nice paper now from 2020 that talks about what happens for square matrices. And he attributes, the core of that argument to Kummert's 1989 paper that gets a dimensionality, a minimality result about the dimension even in this matrix case. And his paper also talks about what happens when phi is rational and not necessarily inner. I know I said I would stick to inner functions, but I just at least wanted to mention this result because I think it's really pretty that in the case of non-inner rational functions, there is a finite dimension contractive transfer function realization, and that's proved to really be a really critical tool when studying bounded rational functions in multiple variables. All right, so that's the rational case. Let's look at more general inner functions. So there is a nice result in the 1-variable case that says that a function is inner if and only if it has an isometric transfer function realization, where the D operator is in C0 dot, or as you provide kind of multiple iterations of D, it goes to 0 in the strong operator topology. And there's some really nice work in the 2-variable setting due to Ramal Dibnath and Jadab Sarkar in a paper they posted to the archive, I think, in 2020, that I think is worth mentioning here. So they showed that kind of one direction of this 1-variable result holds in 2 variables. So if he has an isometric transfer function realization so that the D operator is upper triangular and the diagonal pieces are in C0 dot, then the function has to be inner. But unfortunately, the converse is false, and they provide a nice example using a fairly simple rational inner function. They were also able to use these transfer function realizations to characterize when an inner function is secretly a factor of an inner function in Z1 times an inner function in Z2. And so that's what's showing up here. They show that this happens precisely when there's a co-isometric transfer function realization, again, where the D operator is upper triangular. And now the blocks have to obey this special property here. So I thought this was a really nice result, showing how some properties of the inner function can be reflected in properties of its transfer function realization. Now what I want to talk about is maybe how to take an inner function and get a transfer function realization that where the formulas for the transfer function realization, kind of the A, B, C, and D, are directly linked to the inner function phi. And it turns out we can do that if we make the underlying Hilbert space M come from the extremal Agler kernels that I mentioned earlier that are constructed using the Bal-Zadovsky-Vinnikov argument. So we're going to construct the Hilbert space M by setting M1 to be the reproducing kernel Hilbert space associated to K2 min. So the kind of Z, the S2 min, the numerator of the S2 min kernel, and M2 to come from kind of the S1 max, so the numerator of its reproducing kernel. And then let's define our operator U from C plus M to C plus M. Well, so that it looks like what we saw in the one variable case as much as possible. So what do I mean by that? Well, A and B are going to do what you would expect. So A takes a number and multiplies it by phi of 0. And B takes in a function and evaluates it at 0. And it's actually known, so this was part of that Bal-Bolotnikov paper that I mentioned earlier, that, you know, for any transfer function realization, I think you can always pull out the fact that A and B have to have this particular formula. But kind of the interesting thing here are the C and D operators. So remember in the one variable case, C took a number and multiplied by the backward shift of phi, and D took F and took its backward shift. So this is kind of an interesting two variable analog. So here for C, we'll feed in the inner function phi, take its backward shift in Z2 and project onto M2. We'll also take phi, take the backward shift in Z1 and project onto M1, and then add those two functions together. So this is the backward shift version in two variables. And we do basically the same thing to define D. We just apply that backward shifting and projecting operator to the F we've extracted from the Hilbert space M instead of to the inner function phi. And so it turns out that this U that I wrote up is a co-isometry. And if we define EZ in the same way as before, so you kind of take a function, split it into something from M1 and M2 and multiply 1 by Z1 and 1 by Z2, then this gives us a transfer function realization of phi. And so some of this appeared in a paper that I wrote with Greg Neese. And the operator, the formulas for C and D appear in a more recent paper with Pascoe and Tully Doyle. As I mentioned earlier, this connects to work of Bal and Bolotnikov. And it also connects to kind of more general work done by Bal, Kalyutsniger, Bovetsky, Sadowski, and Vinnikov in 2005, where they do some similar type of construction using formal reproducing kernel Hilbert spaces in the land of kind of general Agler decompositions for sure Agler functions on the polydisk. And I didn't really see a way to get kind of from their work directly to this. Our arguments are very like kind of straightforward Hilbert space type decomposition arguments, but there's definitely some relationship between the formulas that they get and what we're seeing here. All right, so the critical thing here is that now if we have an inner function, we have a pretty concrete transfer function realization formula where everything kind of ties back to phi. And so we can ask the same question about regularity on the boundary. I think I'm going to skip talking about this 2013 result since I lost a little bit of time when I cut out. And I really want to focus on this open question at the bottom. Because in the one variable case, we saw that phi extending to an arc on the unit circle was equivalent to the realization extending to that arc. And really the question that when I say we, I mean Pascoe and Tully Doyle and me, we're trying to answer is, when does this generalize to a rectangle on the 2 torus. So if phi extends continuously to a rectangle, does the realization extend to that rectangle as well? And unfortunately, this is still an open question. This has turned out to be kind of intractably challenging. But I do want to tell you about a special case that we were able to handle. Specifically, dealing with what are called quasi-rational functions. So a quasi-rational function is basically a function so that instead of extending continuously to a rectangle on the 2 torus, it extends continuously to a strip, so to the torus cross an interval. So we impose this stronger regularity condition. And so one way to kind of construct these quasi-rational functions are to take rational inner functions in Z1 and Z2, and for the second coordinate, so kind of what I'm doing here, plug a 1 variable inner function in for Z2 instead of simply kind of Z2 itself. And that process will typically give us a quasi-rational function. And really intuitively, the idea is that these are inner functions that are rational in one of the variables. And so basically what we were able to show is that if we restrict to quasi-rational functions, then the regularity of the model or of the realization exactly reflects the regularity of the inner function. So what this result here is saying is that if I have a quasi-rational function that extends to t cross I, so to a strip with width I, then the critical piece of the realization, this inverse operator, is well defined on that strip, which means that the realization formula extends to that strip as well. And so at least in the setting of these quasi-rational functions, we have realizations that we can move to the boundary, which ends up being kind of a critical piece of attacking a problem regarding matrix monotonicity. So in my last 9 or so minutes, I want to tell you, I guess, a little bit about why we were so interested in pushing our realizations to the boundary and why one might be interested in kind of returning to that open question about if an inner function is analytic on or continues to a rectangle, does its realization continue there as well? All right, so let's look at this. All right, so we need to switch gears here for a moment because I just need to tell you about this matrix monotonicity problem, and then you'll see later where the realization for quasi-rational functions comes in. Okay, so switching gears, let's let E be a convex set in R2. So we're still in 2 variables. And let's let F be a function that takes E to R, to the real line. Well, then we can extend F to pairs of commuting matrices in kind of the straightforward way. So let's say that A1 and A2 are commuting matrices and their joint spectrum lies in the convex set E. Well, since A1 and A2 commute, they can be diagonalized with the same unitary. So this means that we can match up their eigenvalues in an appropriate way. And then we can define F of A by simply diagonalizing and applying F to these eigenvalue pairs, or equivalently to the pairs in the joint spectrum of A. Well, then we say that this function is globally matrix monotone on E if it preserves matrix inequalities. So if whenever A1 is less than B1 and A2 is less than B2, in the sense of matrix inequalities, then F of A is less than F of B. Now, in that 2012 paper that I mentioned earlier, with the refinement by James Pascoe in 2019, Agler, McCarthy, and Young basically characterized functions that preserve matrix inequalities, but they had to do it in a local sense. So basically, they showed that a function mapping this convex set E to R preserves matrix inequalities along curves in E, if and only if F analytically continues to the bi-upper half plane as a map that takes the bi-upper half plane back into the upper half plane. And these are classically called pick functions. Now, it would be nice to change local to global here, because this local condition is a little bit more complicated, and it does appear to be weaker than the global condition. So let's kind of think about what's missing. Well, what this is saying, so what we can extract from this is that if you have a globally matrix monotone function, it's certainly locally matrix monotone. So it does extend to a pick function. However, if you have a pick function that, say, restricts and is real valued on E, then this result tells us that it's locally matrix monotone, but we don't necessarily know whether it's globally matrix monotone. So John McCarthy kind of encoded this missing piece in the McCarthy-Champagne conjecture, which conjectures that if you start with a pick function that analytically continues across one of these convex sets and is real valued there, then that restriction should be a globally matrix monotone function. And so that's the problem that we were trying to attack using this theory of realizations. And we were able to get a partial answer. Okay, so just remember quasi-rational inner functions are inner functions that extend continuously to a strip on the two torus, a strip of the form, the unit circle across an interval I. Now we simply need to move these quasi-rational functions to the setting of, well, the matrix monotonicity problem. So we need to move the bi-disk to the bi-upper half plane, which will then move the two torus to R2. And the way you do that is using the Cayley transform there. All right, so here's what we were able to prove. So we start with a quasi-rational function, with respect to an arc I, or equivalently extending continuous to some t cross I. And then we define our new function f to be just phi composed with the Cayley transform and its inverse. Now pick any rectangle contained in R cross alpha of I. So basically this is what happens when you take this strip on the two torus and move it over to R2. You get a strip of some width in R2. If we pick a rectangle in that where f is well defined, so notice, where are we getting f? We're plugging phi into alpha. Alpha blows up at 1. So you have to kind of avoid the places where phi was hitting the value 1, because then f blows up. But if you pick rectangles that avoid those spots in this strip in R2, then f is globally matrix monotone on those rectangles. And I think I still have 2 minutes, so I'm gonna be able to finish here. Well, the proof idea is the following. So our quasi-rational function has a nice two-variable realization, and the critical piece of information is that it extends to the strip on the boundary. And the idea is that you transfer this realization to the bi-upper half plane to get a realization for, well, first for f, but then you actually switch to an f tilde, where you don't just have a realization in the bi-upper half plane, you have a realization on this whole rectangle in R2. So you kind of have to change f a little bit so that the kind of nice part of the boundary is now this whole rectangle. Well, it turns out that now this realization for f is nice enough that we can lift f to a non-commutative function with good behavior on, a nice part of the boundary of its domain, and use non-commutative results that were due to James Pascoe and Ryan Tully-Doyle to actually, like a version of Loebner's theorem in the non-commutative setting, to conclude that the non-commutative version of f tilde preserves matrix inequalities, and then knock that back down to f, and then transfer, and then use that kind of immediately to get that f is globally matrix monotone on the set E. And I'm going to brush all of those details under the rug because this is not a non-commutative kind of free analysis week. And then, some open questions remain. So kind of the critical open question is, if our inner function extends continuously or analytically to a rectangle in the two torus, can we extend the realization there? Can we conclude that, oh, it's not written here, but I minus e tau d inverse is a bounded linear operator? We can show that it has dense, that I minus e tau d has dense range. We have not been able to show that it's bounded below. So that's really the piece of the argument that's missing. And if you could fill in that piece, then we could prove more or less the entire McCarthy-Champagne conjecture, at least on rectangles, not a general convex set. And then there's some other kind of questions here, but I think looking at the clock, it's 11:50, so I'll stop there. Thanks for listening.
Thank you. Let's thank the speaker. Any questions, comments, suggestions? You can post them in the chat or just shout them out. Well, I don't see any questions. If there are no questions, let's thank speaker again. And we have 9 minutes before